So in the first and second part of this video lecture, we have seen the definition of measurable functions. The composition of measurable functions is a measurable functions. We have explored the notions of pullback of a sigma algebra and push forward of a measure. And now we move to establishing a criterion of measurability. So a criterion that a function should satisfy in order for us to conclude that it's measurable. So when, again, a quick review, a function is measurable if the pre-image of measurable sets is measurable. Composition of measurable functions is measurable. And finally, this magic diagram here, which says from a simple object, such as a function, which does nothing but associate points of one sample space to points on the other sample space. Using that function, we can construct a map, a pullback map, that will take a sigma algebra from the target space and give us a sigma algebra on the source space. And we have also seen the push forward, which is a map that will take a measure on the source space and give us a measure on the target space. So we see always this pattern. The function maps points from source to target. The pullback takes a sigma algebra from the target to the source. And now the push forward, it maps a measure from the source to the target. And now we conclude this lecture by establishing a measurability criterion, which says the following. In order for a function f that goes from a sample space to another space, in order for it to be measurable, it is enough that the pre-image of any set in a certain class is measurable on the source space, and with this, as long as this class E generates all the sigma algebra F2 of the target space. And the proof would go as follows. Let us define this family G to be all the subsets of the target sample space, all the subsets whose pre-image is in F1. Of course, by assumption, the family E is contained in G. And now we want to prove the following. We want to prove that G is a sigma algebra. And indeed, this is enough to prove the lemma. And why is that? That would be, of course, because G, since it contains the family E, if it's a sigma algebra, that means it also contains the sigma algebra generated by the family E, and that sigma algebra equals F2. And this is exactly what we want to prove. We want to prove that all sets in F2 are such that their pre-image is in F1. That's what it means to be measurable. So this is what we want to prove. Of course, we want to prove this implication, the if part of the lemma. The only if part is immediate. The only if, of course, if it is measurable, then the pre-image of every set in F2 has to be in F1. So this implication, the direct implication, is trivial. So to prove the reverse implication, what we need now is to show this, to show that G is a sigma algebra. So the first property of these three properties we need to check to conclude that G is a sigma algebra. The first one is quite easy. Omega 2 is a member of G because its pre-image is all of omega 1, and omega 1 is a member of F1 because F1 is a sigma algebra. Now for the second property, we take any set A in this family G, and we note that by definition the set A being a member of the family G means exactly that the pre-image of A is a member of this class F1. Now, of course, we want to study what is the pre-image of the complement of A, and we just have to notice that this is the same as the pre-image of A complement. So pre-images and set operations play well together. So the complement of the pre-image is the pre-image of the complement. Let me just point out this complement here is the complement with respect to omega 2, and this complement here is the complement with respect to omega 1. And now the complement of this set, this is a member of F1, because F1, being a sigma algebra, is closed under complements, and F minus 1 of A, we know already, is a member of F1. So we have proved that the pre-image of a complement is in F1, and we can conclude, therefore, a complement is also in G. Finally, let A1, A2, A3, etc. be a sequence of sets in this family G. And so this means the pre-image of these sets are members of the class F1. And what we have to show is that the union of these A's, A1, A2, A3, etc., the union of ANs over N, is also a member of G, which means their pre-image is in F1. And what's their pre-image? The pre-image of a union is just the union of the pre-images. And now this union is a union of subsets of omega 1. Each of these subsets is a member of F1. And since F1 is a sigma algebra, it's closed under countable unions. So this countable union also is a member of F1. And from there we can conclude that the union going from n equal 1 to infinity of an is a member of G. And this concludes the proof of this very important key lemma. To conclude this video lecture, let's state a fundamental fact about measurability, which makes us comfortable about type of function we are used to work with, which are continuous functions. And this is very good news. Continuous functions are always measurable. Okay, so what does it mean for a function to be continuous? Well, we need spaces where we can talk about continuity. So a function that maps one space to another space, but now these spaces, they're not simply sets, they sample spaces. When we talk about continuity, we need some topology or some metric on those spaces. So we assume omega 1 and omega 2 are both metric spaces. And if they are continuous, they are measurable. Measurable in what sense? Well, in order to be continuous, we need to specify a metric. In order to say they are measurable, we need to specify a sigma algebra. And how are these two things related at all? Well, they are related by the fact that we take a sigma algebra, the Borel sigma algebra, which is the sigma algebra generated by the open sets. And to conclude very quickly, how do we prove this lemma? Well, denote by O the class of open sets in omega 2. For every member of O, that is for every open set in omega 2, since F is continuous, the pre-image of that set is an open set of omega 1. This is the very definition of a function being continuous. A function is continuous if the pre-image of open sets is open. And therefore, the pre-image of B is in B1 because it's open, and B1 is the sigma algebra generated by open sets. But now, since B2 is the sigma algebra generated by the open sets, we can go back to the previous lemma. Let's see what the previous lemma is saying. The previous lemma is saying that in order for a function to be measurable, it's enough to show that the pre-image of sets are measurable for sets in a generating family, in a family that generates the whole sigma algebra of the target space. And this is exactly what we have shown here. We have shown that the pre-image of every set B in a generating family is a member of the sigma algebra of the source space. So now we can just apply the previous lemma and conclude that F is measurable.